Welcome to Grandpa's Late Nights. Pull the blanket up a little higher, would you? There. That's better. It's good to have you here tonight, whoever you are, wherever you are. And I do mean that. Wherever you are. Maybe you're tucked into bed with the lamp still glowing soft in the corner. Maybe you're on the couch with the TV light flickering low, or riding home late on a train with your forehead against the cold window. Maybe it's raining where you are. Maybe it's snowing. Maybe it's the middle of a long, hot night, and you've kicked the covers down to your ankles. I'd love to know. Tell me, down in the comments before you drift off, where in the world are you listening from tonight? And what time is it in your little corner of the dark? I read those. I like knowing the porch light's reaching somebody somewhere.
And listen, if you'd like more nights like this one, a quiet like and a subscribe really does help this sleepy little channel keep going. Small creators like me lean on it more than you'd think. And to those of you who've already done that, who keep coming back night after night, thank you. Honestly. Thank you for sitting with an old man and his stories. Now, I'll tell you up front the same as I always do. I've got a long, strange, beautiful story for you tonight, and I'm not going to rush it. Not one bit. We're going to move slow. Slow as honey off a spoon. So if you drift off somewhere in the middle, if your eyes get heavy and the words start to blur, and you slip under before I'm done, that's all right. That's the whole idea. The story will still be here. I'll still be here. You can catch the rest another night. There's no test in the morning. Nobody's keeping score. You don't have to understand a single word of it to let it carry you off. Just let my voice be the quiet thing in the room and let the rest take care of itself. I'll tell you something though, and I'll try not to make it so interesting it keeps you awake. But if it does, well, at least you'll have learned something. That's a fair trade, I'd say. So here's the thing I want to whisper to you first. The one strange little fact I want you to take into your sleep tonight. The universe is young. I know that sounds backwards. We're used to hearing it the other way. The universe is old, ancient, almost beyond counting, 13.8 billion years and all of that. And it is that old. That part's true. But here's the part nobody tells you, the part I find so quietly astonishing that I had to make a whole long night of it. By the clock that actually matters, in the clock that counts the eventful years, the years with stars in them, the years where things happen, we are not at the end of the story. We're not even in the middle. We are right at the very beginning. We are in the bright, brief childhood of the whole thing. Something like 95% of the universe's eventful history hasn't happened yet. It's all still ahead, still future, still empty pages. We didn't arrive late to a finished world, kiddo. We arrived early. We're sitting by a fire that's only just been lit, watching the first sparks go up, and most of the long, dark, quiet night is still to come. There's something lonely in that, I suppose. But there's something tender in it too. We're not the last to the party, we're nearly the first. And while we're talking about strange little facts, here's another one, and this one you can almost reach out and touch. You know the old televisions, the really old ones with the big glass fronts, the kind that hummed and went warm to the touch? When there was no signal coming in, the screen would fill up with that grey, hissing snow. Static. That speckled, restless storm of black and white. You've seen it. You might have even been lulled to sleep by it once as a kid, the TV left on long after the late movie ended. Well, about 1% of that snow, that hiss, that flicker, wasn't coming from anywhere on Earth. It wasn't the station, or the wiring, or the weather. It was the universe itself. It was the oldest light there is, the leftover glow of the very beginning, having traveled for almost the entire age of the cosmos to land, of all places, in your living room, to show up as a little extra speckle on a screen while you waited for the picture to come back. There's a name for that glow. We call it the cosmic microwave background. That's a mouthful, I know. So let's set the fancy words on the shelf for a moment and just hold the picture. Think of it as the universe's first light, gone faint and cold with age. It started out blazing hot, brighter than anything, and over billions and billions of years of the universe stretching out wider and wider, that light got stretched and cooled right along with it. Stretched until it dropped out of the colors your eye can see, down into the gentle hum of microwaves, the same family of waves that warms your leftovers. Today that light has cooled all the way down to about 2.7 degrees above absolute coldness. 2.725 degrees if you want the careful number. That's about as cold as anything gets, just a few breaths above the coldest cold there is. And it's everywhere. It's filling the whole sky in every direction all the time, this faint, cold whisper of the morning the universe was born. You just can't see it with your eyes. But the old TV could feel a little of it. So could the antenna on your roof, if you ever had one.
Isn't that something to fall asleep to, that the afterglow of the entire universe was hiding in the static all along? All right, settle in. Let's go back, way, way back. Back before there was an Earth, before there was a sun, before there was a single star, anywhere to light a single thing. Let's go back to the very beginning, and we'll walk forward from there, slow and easy, all the way to the very end. The whole story, start to finish, in one long, calm night.
Now, to feel the beginning properly, you've got to imagine the smartest people in the world feeling pretty sure of themselves. Because for a long while, that's where things stood. There was a time when the folks who study these things looked out at the heavens and the rules that ran them and thought, more or less, that the picture was nearly complete. A tidy world, a settled world. The forces that pushed and pulled all seemed to be understood, give or take a few small leftover puzzles, a few loose threads nobody had gotten around to tucking in. It felt like a golden afternoon of certainty, almost done, almost solved. It is funny how often the universe waits for exactly that moment, the moment we feel we've got it all figured out, to lean in close and whisper, "Oh, you sweet thing, you have no idea." Because the beginning, when we finally chased the story back to it, turned out to be stranger than anyone's tidiest dream. Let's start at the very edge of what we can even talk about. The first fraction of the first second, and I don't mean the first second the way you time an egg. I mean a sliver of a second so small that there's almost no honest way to picture it. A tiny, tiny, tiny crack of an instant, far less than the blink of an eye, far less than the time it takes a hummingbird's wing to flick once. In that impossibly small sliver of time, something happened that we call cosmic inflation. Let me say that gently because it's a strange one. Inflation. Same word you'd use for blowing up a balloon, and that's not a bad way to hold it. In that flicker of an instant, somewhere in the neighborhood of a billionth, of a trillionth, of a trillionth of a second, a number so small the words pile up and lose their footing, space itself ballooned outward. Not the stuff in space. Space. The very stretch and fabric of everything swelling up faster than you could ever follow. Here's the homely picture for it. Imagine something smaller than a single proton. Now, a proton is one of the tiniest building blocks there is, a speck inside the heart of an atom, far too small to ever see. So small that millions upon millions of them could hide on the tip of a pin and you'd never know. We're starting with a patch of the universe smaller than even that. And in that one impossible flick of time, that speck stretched out until it was larger than a grapefruit. From less than a proton to bigger than a grapefruit, in less time than I can hold in a word. I know that doesn't sound like much. A grapefruit. You could hold one in your hand, but you have to feel the leap, not the finish line. The patch grew by a factor, a stretching of something like 100 billion. Written out plain, that's a 1 with 26 zeros trailing after it. Imagine starting your savings with a single penny, and then, in less than a heartbeat, your account has a 1 followed by 26 zeros. That's the kind of swelling we're talking about. Everything we can now see, the entire reach of stars and galaxies, the whole observable everything, was once tucked into that tiny, smooth patch that suddenly bloomed. Now, I'll be honest with you, because that's the only way I know how to tell a true story. Inflation is our best leading idea for those first moments. The math sings, the picture fits the clues we find written across the sky. But we haven't directly caught it in the act. There's a kind of confirmation we're still hoping to find, a particular ripple it should have left behind, and we're still listening for it. So when I tell you the universe ballooned from a speck to a grapefruit, hold it the way you'd hold a beautiful, well-supported guess. The best story we have, not yet, the closed book. That honesty is part of what makes the whole thing trustworthy, I think. The people who study this don't pretend to know what they don't. So, we've got our grapefruit-sized, blazing hot, newborn patch of everything. And it is hot. Hotter than hot. Hotter than anything that word has ever meant. So fiercely, ferociously hot that the ordinary furniture of the world, the atoms, the bits inside atom, none of it could exist yet, couldn't hold together. It was all just a roaring, seething soup of pure energy in the very simplest specks, far too wild and hot to settle into anything you'd recognize. And here's a lovely thing about those first moments. The way the universe works, the forces, the pushes and pulls that run everything, it didn't always look the way it does now. Today we count 4 great forces in the world. There's gravity, the gentle, patient one that holds you to your bed and holds the earth to the sun. There's the force that lets magnets cling and electricity flow and light travel. Call it the electric one. And then there are 2 shy ones, 2 forces that only ever show their faces deep, deep inside the heart of an atom, far too small for us to feel directly. One that glues the very center of an atom together, and one that lets certain things quietly fall apart and change.
4 forces, but in that first searing instant, the smart money says they weren't 4 at all. They were one, a single, unified force, all woven together into one thing, the way white light is all the colors braided into one beam. And as the universe cooled, and it cooled fast, the way a struck iron cools as it stretches thin, those forces froze out of the oneness, one at a time, like different things crystallizing out of the same cooling pot at different moments.
Gravity stepped out first, going its own quiet way. Then the strong one, the gluey center of the atom force, settled out next. And then the last 2, still joined for a while, finally parted ways into the electric force and that shy little changemaker. One by one, the single force becoming the 4 we know, settling, separating. The universe finding its rules as it cooled, the way frost finds its shapes on a window pane on a cold morning. I find that one peaceful, somehow. The idea that everything that pushes and pulls in the world was once a single thing and only came apart as the heat went out of the morning. Now let's let a little more time pass. Still less than the blink of an eye, mind you. We're still inside the first breath of the first second. The universe at this point is a kind of soup. And I want to tell you about this soup because we've actually tasted it. Sort of. I'll get there. You know how everything around you, everything solid, this blanket, your hand, the walls, the stars, is built from tiny building blocks called atoms. And the very center of each atom, the dense little seed at the heart of it, is made of even tinier pieces, two of them in particular, that you've probably heard named the proton and the neutron, the two little weights packed in the middle. Well, those little weights are themselves built from something smaller still. Smaller pieces with a funny little name, quarks. Just a silly word somebody borrowed from a poem, but that's the name and that's all they are. The tiniest grains we know of, the grains that clump together to make the protons and neutrons that make the hearts of atoms that make the stuff of everything. Today, those quarks are always locked away. Always bound up, three at a time, tucked tight inside the protons and neutrons, never running loose. You'll never catch a lonely quark wandering around on its own. They're shy that way, glued in for good. But in that first sliver of the universe, for the first 10 millionths of a second, give or take, it was simply too hot for them to clump. Way too hot. The heat shook everything apart faster than it could ever stick together. So the quarks weren't locked inside anything. They roamed free, all of them, a wild and rolling sea of loose grains and the glue that would one day bind them, all of it flowing and churning together. We've got a name for that state, that hot, free-flowing soup. The quark-gluon plasma. Don't let the word spook you. Just picture a fog so hot and so fine that none of the droplets have yet found each other to join up. A storm of loose ingredients before the recipe. And now here's the part I promised. The part that gives me chills, even at my age. We have made some. We have, with our own hands, on this little earth, briefly recreated a tiny droplet of that very first soup, down inside enormous machines built for exactly this. There's a great ring of a thing called the Large Hadron Collider, buried in a tunnel that runs for miles, and another like it that goes by the name RHIC. Clever people take tiny bits of matter and smash them together at nearly the speed of light. And in that little collision, for the smallest flicker of time, the heat gets so fierce, so concentrated, that the quarks come unglued again. For just an instant, in a spot smaller than you could ever see, they've brewed up a fresh, tiny drop of the newborn universe. A bead of the morning of all things, made on purpose, in a lab, and then gone again before you could finish saying its name. Think about that as you're lying there. People built a machine to make a droplet of the beginning of time. And it worked. We held a spark of the first 10 millionths of a second in our hands, just for a flash. There's no end to what curiosity will reach for. All right, let's let the soup cool a touch more and tell you about a mystery, a real, honest, still unsolved mystery. That's the only reason you and I are here at all, to talk about any of this. In that early roaring fog, things were coming into being and winking out constantly, and among them came a strange pairing. For nearly every kind of tiny particle the universe makes, there's a sort of mirror twin, an opposite version of it. We call that opposite kind antimatter. And when a particle meets its opposite twin, the two of them don't fight exactly, they embrace, and in embracing they vanish. Both of them gone in a single flash of pure light. They cancel each other out completely. Snuffed like a candle pinched between two fingers, leaving only a little glow behind. So in those first moments, matter and its mirror twin antimatter were being born together in great matched pairs and meeting and annihilating over and over and over. Flash, flash, flash. A war of mutual disappearing fought across the whole young universe, and here's the trouble. If it had been a perfectly even fight, exactly as much matter as antimatter, then every single bit would have found its twin and vanished, and the universe would have been left with nothing at all but light. No stars, no worlds, no quarks left to clump, no atoms to build, no you, no me, No blanket, no late-night porch light, just light, racing through an empty everything forever. A clean, bright, lonely nothing. But here we are, so the fight wasn't perfectly even. For reasons we genuinely do not fully understand, and I want you to hear that clearly, because it's one of the great open puzzles, one nobody's solved, there was the tiniest imbalance baked into the deck. For roughly every billion pairs of matter and antimatter that met and annihilated and vanished into light, there was about one extra speck of matter. Just one in a billion, one little grain with no twin to cancel it, left standing when all the flashes died down.
And that's it. That's all of it. Every star you have ever seen, every grain of sand on every beach, every drop of every ocean, this whole solid world, and the iron in your blood and the calcium in your bones. All of it, everything that is, was built from that leftover 1 in a billion surplus, the crumbs that survived the great annihilation. We are, all of us, made from the tiny mistake in the count, the rounding error that the universe never tidied up. And nobody yet knows for certain why the count came out crooked in our favor. We see that it did. We're the proof. But the reason is still out there, waiting, a loose thread nobody's managed to pull. I rather love that there are still such things waiting to be understood. It means the story isn't over, not by a long, long way.
So now picture the dust settling, in a manner of speaking. The great war of vanishing is mostly done. The light from all those countless annihilations is still racing everywhere, filling the young universe with a fierce glow. And in among it all, drift the survivors. That thin scattering of leftover matter, the 1 in a billion crumbs, the loose quarks at last beginning to feel the chill enough to clump together into the first proper protons and neutrons, those little weights that will sit at the hearts of atoms someday. But it's still far too hot and too wild for proper atoms yet. We're getting there, we're cooling. Be patient with it. There's no rush tonight, none at all. Let it cool slow. Now we come to a stretch I've always found rather homely and sweet in its way, because it's the part where the universe first starts cooking, truly cooking. The first kitchen the cosmos ever ran, somewhere between roughly 10 seconds and 20 minutes after the very beginning. And isn't that a thought, that the whole of this next bit takes about as long as it take you to soft boil an egg and butter some toast? The universe had cooled just enough for those fresh little protons and neutrons to start sticking together, joining up, clumping into the very first nuclei, the first true seeds at the centers of the first true atoms to be. The fancy name for this little cooking session is nucleosynthesis, but all it means is the universe forging its first ingredients out of the raw stuff, its first recipe. And it was a simple recipe. The universe was a young cook in a great hurry, and the kitchen was cooling fast under its feet. It only had a few minutes before the heat dropped too low to fuse anything more, so it made the simplest things it could, and then the window slammed shut. What it made, mostly, was the lightest and simplest stuff there is. The lightest gas of all, the one that fills the sun, and that we float in party balloons, and that lifts the very simplest atom.
Hydrogen, that's the lightest. About 3/4 of everything by weight came out as that. And the next simplest after it, a touch heavier, about 1/4 of everything. And then the faintest trace, just a whisper of one more after that, the third lightest thing, and then that was it. The kitchen had cooled too far, the fire was out, the cooking stopped.
3/4 of the simplest, 1/4 of the next, a trace of the third. And here's a quiet little wonder for you, when we look out at the oldest, most untouched gas in the farthest reaches of the heavens, the ancient stuff that's never been cooked over again inside a star, that's almost exactly the mixture we find. 3 parts to 1. Just as the recipe predicted, written down by people who never saw it happen, worked out from the rules alone, and then confirmed by looking. That's one of the strongest reasons we trust this whole story of the beginning. The universe left its recipe card lying out in the open all across the sky, and the numbers match. They match beautifully. So picture where we stand now. The first 20 minutes are done. The great heat is fading. The war of vanishing is over. And we're the lucky crumbs. The first simple ingredients are cooked and floating free. A vast, thin, hot fog of the lightest gases. Hydrogen and a quarter share of the next, glowing, drifting, spreading out wider and wider as space keeps gently stretching. No stars yet, none, not a single one, no planets, no light to read by, no warmth from any furnace. Just that hot, bright, simple fog filling everything, cooling slowly, slowly, slowly as it goes. And that fog is still far too thick and too hot to see through. That's the thing to hold as you start to drift. The whole universe at this point is glowing. But it's a fog you couldn't see across, like trying to peer through the inside of a cloud lit up from within. Bright, but blind. The light can't fly free. It keeps bouncing, bumping, scattering off all the loose little bits crowding the fog, never getting anywhere, never breaking out. The universe is luminous, and yet you couldn't see your hand in front of your face in it. For a long time, a long, long stretch of cooling, it stays that way, a glowing, blinding fog, thinning and dimming as the everything keeps stretching wider beneath it. And somewhere far ahead, in that cooling fog, there's going to come a moment, a great, quiet, world-changing moment, when at last the fog clears, when the light finally gets to fly free for the first time, racing off in every direction across a universe gone suddenly beautifully transparent, the moment the lights, in a sense, come on. The very first light ever set loose to travel, and the same ancient glow that's still out there now, cold and faint, the very glow that hides in the static of an old TV. But that clearing is still a good while off. The fog has cooling left to do, and we've all the time in the world, you and I, so let it cool, let it thin, let it drift. Rest your eyes a moment if they're heavy. I'll keep going, soft and slow, and I'll be right here when the fog finally clears. Now, before we drift any further into that cooling fog, let me say a quiet thank you. If you find these slow nights help you settle, a gentle like and a subscribe really do help this little porch stay lit. Small channels like mine lean on it more than you'd think. And I'd love to know, before you nod off, where in the world are you listening from tonight? What hour is it where you are? Leave it down below if you like. No rush. And if your eyes close before the end, that's just fine. The universe will still be here. The story will keep. You don't have to follow every turn. Just let the warmth of it wash over you and drift whenever you're ready. So, where were we? Right at the very, very beginning, before even that fog. There's a notion, and hold it loosely because the deepest parts are still being worked out, that at the start, in the very first unmeasurable slice of a second, the universe got bigger faster than it ever has since, or ever will again. They call it cosmic inflation, and the numbers are the kind your mind can't quite hold, so don't try to. Just picture it. A patch of space smaller than a single proton, smaller than the tiniest speck inside the tiniest speck of anything you could ever name, stretched in a flicker of time so short it barely counts as time at all, into something about the size of a grapefruit, smaller than a proton to a grapefruit, in far less than the blink of an eye. That's a stretching by a factor of around 10 to the 26th, a 1 with 26 zeros trailing behind it. The There's no real way to feel a number that large. So don't feel it. Just let it be enormous and let it pass, the way you'd let a train roar by in the dark and not bother counting the cars. And in those first wild moments, the universe was so hot, so impossibly hot, that everything we now think of as separate was all tangled together as one. You know how, in our cool and settled world, there are these different forces. The pull of gravity holding you in your bed, and the things that hold the bits of atoms together, and the spark of electricity, and the quiet force that lets stars shine. In the beginning, the heat was so great that those forces weren't separate at all. They were folded into one another, indistinguishable, a single thing. And then, as it all cooled, they began to part ways. One by one, like ice forming on a pond as the cold deepens. First a skin, then a sheet, then solid. Gravity slipped away first, settling out on its own. Then the strong force, the one that would one day glue the hearts of atoms together. And then the last two, the electric and the weak, peeled apart from each other later still, freezing out one after another as the everything cooled. No drama, no sound, just a slow settling into the separate forces that quietly run the world you're lying in right now. And the stuff of the universe in those earliest moments, it wasn't anything you'd recognize yet. No atoms. Not even the little pieces that make up atoms, not bound together the way they'd come to be. For the first 10 millionths of a second or so, it was too hot for any of that. The tiny things we call quarks, the things that would later clump together into the protons and neutrons sitting in the core of every atom in your body, they couldn't clump at all. The heat kept tearing them loose, so they drifted free, unbound in a kind of hot soup, a quark gluon plasma they call it, the thickest, hottest soup there ever was, thicker than anything that's existed since. And here's a thing I find lovely, lying here thinking about it. We've made that soup again. Right here, in our cool, quiet age, in great machines built by patient people. One called the Large Hadron Collider, another called RHIC. Scientists have smashed bits of matter together hard enough, hot enough, to make tiny, fleeting droplets of that very plasma. The newborn universe, recreated for a flicker in a laboratory. A little drop of the first 10 millionths of a second, cooked up on purpose by curious hands. We made the beginning, just for an instant, to see what it was like. Isn't that something to drift off on? Now, in all that hot soup, something happened that we still don't fully understand. And I'll be honest with you about that, because the not knowing is part of the wonder. There was matter in there, and there was also its strange mirror opposite, what's called antimatter. And the rule, near enough, is this. When a bit of matter meets a bit of its opposite, the two cancel out. They vanish. They turn into light and are simply gone, both of them, like two waves meeting and flattening to stillness. And in the beginning there was very nearly the same amount of each, very nearly, but not quite. For every billion pairs that met and cancelled and flashed away into light, for every billion that wiped each other out, there was one extra little bit of matter left over. Just one in a billion, a tiny, lonely surplus that had no opposite to cancel it. And that's all that was left when the great cancelling was done. That 1 in a billion remainder. That faint surplus is everything. It's every star you've ever seen, every drop of every ocean, every mountain, every breath, every person who ever lived, and you right now warm under your blanket. All of it built from the scraps that by some small lopsidedness no one has fully cracked yet, simply didn't get cancelled out. Why there was that surplus at all, why matter won by that thin sliver, is one of the questions still sitting open, unanswered, waiting. And I think there's a strange comfort in that. We exist because of a leftover, a rounding error, in the books of the beginning. The rest turned to light and flew away, and we are what stayed. And as it kept cooling, those quarks that were left could finally settle and bind. The soup thickened into the first proper building blocks, the protons and neutrons. And then, in a window of time so short it would fit inside a coffee break, somewhere between about 10 seconds in and 20 minutes in, the universe did its first real bit of cooking. It fused those building blocks together into the very first true centers of atoms, the first nuclei, and it made, in the main, two things. Hydrogen, the lightest and simplest there is, about 3 parts in 4, and helium, about 1 part in 4, with only the faintest whisper of anything heavier, 3/4 hydrogen, 1/4 helium, near enough, fixed in those first 20 minutes, and then locked in place. Because after that brief window, the fog had cooled too far to fuse anymore. The oven, you might say, switched off, and the truly marvelous part, the part that lets us trust this whole quiet story, is that when we look out at the oldest, simplest gas in the farthest reaches today, we find very nearly exactly that. 3 parts hydrogen to 1 part helium. Just as the first 20 minutes would have made it. The recipe written in those opening moments, still legible all these billions of years later, out there in the dark, for anyone patient enough to read it. So that's the pantry stocked. Hydrogen and helium, the raw stuff of every star that would ever shine, laid down in the first quiet 20 minutes of everything. And still, remember, all of it wrapped inside that hot, glowing, blinding fog. The light, still trapped, still bouncing, still unable to break free. The ingredients are ready, the oven's cooling, and the great clearing, the moment the light at last gets loose. That moment is still waiting, just ahead. So let's go there now. Let's follow the universe forward a little more slowly from that dense, humming fog into the first true quiet. Imagine you are inside it. Not looking at it from outside, actually, that's not possible, but inside it, surrounded by it. In every direction, a glowing, churning, opaque warmth, not darkness, brightness actually. A fierce, deep, red-orange glow, the color of very hot iron fresh from a forge. The universe was not dark at first. It was bright, brilliantly, blindingly bright. But that brightness was trapped. Every photon of light, every little packet of energy trying to travel would shoot off in some direction and almost immediately slam into a free electron, bounce away, shoot off in another direction, slam into another electron, bounce, deflect, scatter. The universe was a fog so thick that light, the fastest thing there is, couldn't travel more than a tiny distance in any one direction before being knocked sideways again. It was like trying to see across a room that's completely filled with thick smoke. This went on for a long time. Not a moment, not an hour, not a year. A very, very long time. 380,000 years. When you hear that number in a story that has been talking about 10 to the minus 32 seconds and the first 20 minutes, 380,000 years sounds almost comfortable, almost human scale. And in cosmic terms, yes, it is relatively brief, a blink compared to what comes after. But in any ordinary sense of time, it is an almost incomprehensible stretch of waiting. All the while, the universe kept expanding, kept stretching itself thinner, kept cooling. Degree by degree, the temperature dropping from millions of Kelvin down through the tens of thousands, creeping steadily towards something calmer. And somewhere around 3000 Kelvin, roughly half the temperature of the surface of our own sun today, is something changed, something very quiet and very decisive. The electrons slowed down enough The protons and helium nuclei, which had been trying for hundreds of thousands of years to hold on to their electrons, finally could. The energy in the environment was no longer fierce enough to keep ripping those electrons free. And so, in what physicists call recombination, a slightly misleading name since the electrons and nuclei had never actually been combined before, the electrons and nuclei came together for the first time into complete, stable, neutral atoms. Hydrogen atoms, helium atoms, whole atoms finally, made of their proper parts. Now, here is what that means for the light. When the universe was full of free electrons, every photon was bouncing off something every tiny fraction of a second, unable to travel. But neutral atoms don't do that. Not in the same way, not to the same light. Neutral hydrogen in particular is largely transparent, the kind of light the universe was full of at this temperature. And so the moment those electrons settled into their atoms, the fog cleared. All at once, across the whole universe, the light was released. Every photon that had been trapped and bouncing and scattering for 380,000 years was suddenly free, and it streamed outward in every direction, traveling in straight lines at last, uninhibited, across a cosmos that had just, for the first time, become transparent. Physicists call this moment the surface of last scattering. That name means exactly what it says. It is the moment when light last touched matter on its way to us. Everything we see with our eyes or our telescopes, when we look out into the deep universe, all of it is light that has traveled a clear path to reach us. And when we look as far as our instruments can possibly see, we run up against the edge of what was transparent. We see at the farthest reach of observation the surface of last scattering, the last wall of fog, and the light from that wall, the light that was released when the universe first cleared 380,000 years in, is still traveling. It is still here, right now. As you're lying there, that ancient light is passing through the walls, through the ceiling, through you. It is everywhere, coming from every direction equally, the oldest light in existence. We call it the cosmic microwave background, the CMB, and here is one of the loveliest, most quietly astonishing facts in all of science. In the middle of the 20th century, if you had an old analog television, the kind with a physical antenna, the kind that would show static when it wasn't picking up a broadcast, and you tuned it to a channel that wasn't broadcasting anything, some of that static, something like 1% of the little dancing snow on the screen, was this: light from the Big Bang. Light that had been traveling for 13.5 billion years, finally reaching your living room, getting picked up by your antenna, along with all the other noise, and ending its journey as a faint flicker of static on a television screen. The oldest light in the universe in your living room on an ordinary Tuesday evening. Penzias and Wilson stumbled onto it in 1965. Arno Penzias and Robert Wilson, working at Bell Labs in New Jersey with a large horn-shaped radio antenna originally built for satellite communications. They were trying to do careful, precise radio astronomy, but there was a problem. There was a faint, persistent background noise coming from their equipment. A soft hiss, picking up signal from every direction in the sky equally. They couldn't get rid of it. They recalibrated their instruments. They checked their connections. They did everything careful scientists do when something won't go away. And then they looked inside the antenna's horn and found, if you'll forgive the detail, that a pair of pigeons had been nesting in it and leaving behind what Penzias and Wilson diplomatically described as white dielectric material. Pigeon droppings. They cleaned the antenna. The hiss remained. It wasn't the pigeons. It wasn't instrument error. It wasn't radio interference from New York City. It was the universe itself whispering, the afterglow of recombination, still faintly warm, arriving from every direction in the sky with equal intensity, a bath of ancient microwave radiation that fills all of space. They had detected the cosmic microwave background. The discovery won Penzias and Wilson the Nobel Prize in Physics in 1978, and that persistent, unexplained hiss became one of the most profound measurements in human history. The CMB today has a temperature of 2.725 Kelvin, 2.725 degrees above absolute zero. Cold, impossibly cold, the chill of a universe that has been expanding and cooling for nearly 14 billion years. But when Penzias and Wilson first measured it, they weren't even sure that's what they had. It was only when they heard that a group of theorists at Princeton, Robert Dicke, Jim Peebles and their colleagues, were actually looking for exactly this signal, were actively preparing an experiment to try to detect the leftover light from an early hot universe, that everything clicked into place. The experimenters and the theorists working independently arrived at the same conclusion from different directions. Now, there is something else about the CMB that matters tremendously, something that took decades of increasingly sensitive instruments to measure properly, but which, when measured, revealed the blueprint of everything that would come after. The temperature is not perfectly uniform, almost, but not quite. Across the whole sky, the CMB temperature varies, but only by about 1 part in 100,000. Tiny, tiny variations, regions that are almost imperceptibly slightly hotter, and regions that are almost imperceptibly slightly cooler. A map of the CMB looks like a nearly featureless warm oval, but zoom in, magnify the variations, and you see a delicate mottling, slightly denser patches and slightly thinner patches left over from quantum fluctuations in the earliest instance of the universe, the tiny ripples that inflation stretched and amplified across the cosmos. Those ripples, those 1 in 100,000 variations, are the seeds of everything. Wherever the primordial gas was ever so slightly denser, gravity was ever so slightly stronger. Matter drifted in toward those patches. Over millions and then billions of years, those tiny density differences grew. The denser regions pulled in more matter, which made them denser still. Filaments and sheets and voids began to form, and eventually, the densest knots collapsed into the first stars. All of that future structure, everything that would ever shine in the sky, was written into that ancient, almost uniform afterglow. The universe announced its future in whispers so quiet we only learned to hear them properly in the late 20th century. But between the CMB and those first stars, there is a chapter of cosmic history that doesn't get talked about nearly enough. A long chapter. A dark one. After the light was released, after the surface of last scattering, the universe was full of neutral hydrogen and helium gas. No stars, no galaxies, no sources of light at all. The CMB itself was cooling, its light stretching to ever longer wavelengths as space expanded, shifting out of the visible range, fading from the fierce red-orange glow of the clearing moment into infrared, into microwave, into the faint whisper it is today. The light from the Big Bang's clearing was still there, still filling space, but it was fading and cooling and invisible to any eyes that might have been present, which there weren't. The universe entered what cosmologists call the cosmic dark ages. Think about that phrase, the dark ages, the whole universe dark. Not just a cloudy night, not just an area without electricity, the entire universe in every direction, at every scale, for an enormous stretch of time without a single source of light. Just cool, dark, neutral hydrogen gas slowly drifting in the vast, stretching dark. The occasional helium atom, gravity quietly doing its patient work, pulling the slightly denser regions infinitesimally tighter. This went on for somewhere between 100 million and a couple 100 million years. The exact moment when the darkness finally broke is something astronomers are still working to pin down precisely. It falls in what's called the epoch of reionization, and we don't have a sharp edge on it yet. But for something like 100 million years, perhaps somewhat longer, the universe was simply dark. No candle, no ember, no faint star on the horizon, just the cooling dark. And if that sounds a little lonely, a little desolate, well, yes, it is. But there is something almost peaceful about it too when you let yourself imagine it properly. Not a violent darkness, not a frightening one. A cool, quiet, spreading dark, with hydrogen atoms drifting slowly in the vast spaces between the gravitational seeds of what would one day become everything we know. The universe at rest, in a way. Potential, not yet expressed. Then, somewhere around 100 million years, perhaps a bit more, the estimates shift as we get better data, the first stars switched on. We have never seen them directly, not one. They formed in an era still mostly opaque to our best telescopes. The James Webb Space Telescope is pushing back further than anything before it, catching the faint signatures of very early galaxies. And perhaps in the years to come we'll get something closer to a direct glimpse. But right now, the very first stars remain just beyond our observational reach. We know they existed. We know from the physics of what was available to them and the physics of how stars form quite a bit about what they must have been like. But we have not yet seen one, not directly. What we know is this: the gas that formed those first stars was the pure, untouched output of Big Bang nucleosynthesis. The 3/4 hydrogen, 1/4 helium recipe laid down in the first 20 minutes that we talked about earlier. No heavier elements, nothing else, no carbon, no oxygen, no iron, no calcium. None of what we might think of as the rich complexity of ordinary matter. Just the two lightest, simplest elements in the periodic table. Astronomers use a shorthand for this they call heavier elements. Anything heavier than helium, in astronomical terminology, or metals. It doesn't mean what it means in ordinary life. Oxygen is a metal in this sense. So is carbon, so is nitrogen. It just means anything heavier than the Big Bang made. And those first stars had essentially zero metallicity. They were made of pure, pristine, primordial gas. And the physics of that pure gas made them behave differently from the stars we know today. The stars we're familiar with, our sun, the stars you can see on a clear night, formed from gas that was already enriched with heavier elements from previous generations of stars, and that enrichment changes the way gas clouds cool and collapse. Heavy elements are very efficient at radiating away heat, which means enriched clouds can cool relatively quickly, which means they can fragment into many smaller pieces, which means they tend to form stars of moderate mass. But pristine hydrogen and helium with no heavy element radiators can't cool as efficiently. The collapsing cloud stayed hotter, puffed up larger, and tended not to fragment as much. The result, as best we can calculate, was stars of extraordinary mass, not like our sun with its modest 1 solar mass of material. We're talking about stars of tens of solar masses, perhaps hundreds of solar masses. Some models suggest the very first stars may have been among the most massive stars that ever existed, perhaps approaching 100-200 times the mass of our sun. And massive stars burn brilliantly, ferociously. They shine 100,000 times brighter than our sun, or more. They are hot and blue and glorious, and precisely because they burn so intensely, they burn fast. A star like our sun will live for about 10 billion years. It's been shining for 4.5 billion years already, and it's not even halfway through. But a star 100 times more massive burns through its fuel in a tiny fraction of that. Not billions of years, not millions of years, perhaps just a few million years. Brief in stellar terms, to the point of being almost instantaneous. these enormous, brilliant, metal-free stars, our population 3 stars, astronomers call them, placing them before the later population 1 and population 2 that we can actually observe, blazed into existence and burned their fuel and died, all before the universe was much more than a few 100 million years old. And when they died, they changed everything. Because those first stars, burning at such extreme temperatures, were forging something new in their cores. That's what stars do. The hydrogen at their center fuses into helium. That's the basic fuel of a star's main life. And then if the star is massive enough and hot enough, the helium fuses into carbon, and the carbon into oxygen, and oxygen into neon, silicon, sulfur, all the way up the periodic table in a cascade of fusion reactions, each producing a heavier element and each releasing a little less energy than the last until the core reaches iron. An iron fusion absorbs energy rather than releasing it, so the fusion stops and the core collapses and the star tears itself apart in a supernova. That explosion, one of the most energetic events in the universe, briefly shining as bright as 100 billion suns, scatters everything the star built outward into space. All the carbon, the oxygen, the magnesium, the silicon, the iron, all the elements the star forged in its core over its brief, brilliant life, flung out in all directions into the surrounding gas. And so the primordial gas, which had been pure and simple, became enriched. The next generation of stars formed from clouds that already contained a little carbon, a little oxygen, a little of everything else, and from that enriched gas, different stars, and eventually planets. And eventually, around those planets, chemistry of astonishing complexity, because carbon and oxygen and nitrogen and hydrogen, given enough time and the right conditions, do extraordinary things together. You have, in your body right now, carbon. You have oxygen. You have nitrogen, calcium, iron. There's iron in the hemoglobin in your blood right now as you're listening to this. And none of that existed after the Big Bang. None of it. The universe, fresh from the first 20 minutes, contained essentially none of it. Every atom of carbon in your body was forged inside a star. Every atom of oxygen you breathe was made in a stellar core. The iron in your blood was scattered into space in a supernova explosion billions of years ago before our sun existed. You are, in the most literal and precise chemical sense, made of star stuff. Carl Sagan said that, and it is not poetry. It is nucleosynthesis. It is the verified, measured output of stellar physics. Look at your hand. Every atom, heavier than helium in it, was cooked inside a star that lived and died before the Earth existed. And those first population stars, those enormous, brief, brilliant, nameless giants of the Dark Ages, they were the first Smiths. They made the first heavy atoms in the universe. They died, and they seeded the cosmos with the raw materials of everything that would follow. Now, there is another thing those first stars did, besides forging heavier elements in their cores. They poured out ultraviolet radiation, enormously energetic light blazing from those massive hot bodies, streaming out in all directions into the surrounding gas. And ultraviolet radiation does something specific and important to hydrogen. It ionizes it. It strips the electron back off the atom, turning neutral hydrogen back into a proton and a free electron. Remember that the universe had spent 380,000 years slowly letting its electrons and protons come together into neutral atoms. Recombination, the great clearing, the release of the CMB. Now the first stars were undoing that locally at first, and then, as more and more stars formed, more and more widely, regions of ionized hydrogen, called HII regions in the notation astronomers use, began to form and grow around the first stars and the first clusters of stars and the first galaxies. They expanded and merged bubbles of newly reionized gas spreading outward. This process is called reionization, or the cosmic dawn, and by about 1 billion years after the Big Bang, give or take, the exact timing is still being refined, reionization was largely complete. The hydrogen throughout most of the universe had been stripped of its electrons again. The cosmic dark ages were well and truly over. The universe was alive with light, not entirely uniformly, not all at once, not in a single neat moment. It was a process, spreading and uneven like mold on bread, but in reverse, light winning back the dark in patches and bubbles and expanding regions. But by 1 billion years in, the broad universe was ionized, transparent, and bright with the light of the first galaxies. And those first galaxies themselves? That's where the story gets interesting in a new way, because what we expected when we finally had tools powerful enough to look that far back was something more modest. Something smaller and simpler, the early stirrings of cosmic structure, rough and primitive. That's what the standard models of galaxy formation predicted. That's not entirely what we found. The James Webb Space Telescope, which began returning science data in 2022, has been looking at that early universe, at galaxies only 300, 400, 500 million years after the Big Bang, and it has been finding galaxies that are surprisingly massive and surprisingly well-formed for things that young. Galaxies with more stars than the models expected, organized more like mature galaxies than like raw, early structures. Galaxies that, on the current models, seem to have formed too fast, gotten too big too quickly, before there was quite enough time for the processes we understood to have built them. This is not settled. This is science in progress, science as it actually happens. Data coming in, models being tested, theorists scrambling to understand. Some of the discrepancies may be resolved by better measurements. Some may point to new physics or incomplete models. We don't know yet. But the honest thing to say is that the universe, as seen through the sharpest eyes we've ever built, has been mildly but clearly surprising us. Which honestly is one of the things that makes it so worth paying attention to. And somewhere in all this, somewhere in the first billion years, in the cosmic dawn, in the building of those early galaxies, the universe was doing what it would continue doing for billions more years. Pulling itself together by gravity, forming stars, filling the dark with light. Building the scaffolding of cosmic structure, the vast filaments and sheets and walls of galaxy clusters with enormous empty voids between them, a kind of cosmic web that is itself one of the more startling things you can see in a map of the universe, all of space organized into this delicate, lacy, interconnected structure, like the pattern of soap bubbles in a sink on the very largest scales. So let's just let that settle for a moment. 380,000 years, the universe clears, the CMB is released, light travels freely for the first time. 100 million or more years of darkness. Then the first stars, enormous and brief and brilliant. Then, by 1 billion years in, a universe full of light again, with galaxies forming and growing, stars being born and dying and enriching the gas around them, the first heavy elements dispersing into the clouds that would form the next generation of stars and eventually the first rocky planets. We are, if you'll forgive the slightly dizzying perspective shift, roughly 13.5 billion years downstream of all of that. You are made of the output of stars that lived and died long before the sun existed. Your carbon was forged in a stellar core. Your oxygen was scattered by a supernova. The iron in your blood was cooked at temperatures and pressures we can barely recreate in a laboratory inside a star that burned and died before the Earth had a name or a surface or an orbit. We will get to what comes next, the galaxies growing and colliding and evolving, The cosmic noon, that bright peak when the universe was forging stars at its maximum rate, already, it turns out, far in our past, the present moment, and what it means to be here now rather than at some other point in the timeline. And then the long future, which is where the real surprise of this story lives. But for now, in this quiet, let that first part of the story breathe a little. The universe, 380,000 years old, finally letting the light go free. The ancient glow of that moment, still crossing space today, still passing through you, still detectable in the static of old televisions, still mapped by satellites in extraordinary precision. The long dark that followed, cool and patient. The first, enormous stars flaring into being in the dark and living briefly and brilliantly and dying. And in dying, giving everything that would come after the materials to be more than just hydrogen and helium. The cosmos warming itself, lighting itself, seeding itself with complexity. There is something in that sequence that I find quietly moving, though I can't quite say exactly why. Maybe it's the long dark before the first light, 100 million years of nothing, and then suddenly a star. The first photon not from the Big Bang's clearing, but from fusion. The first nuclear fire lit in the universe by gravity pulling gas together tightly enough. Somewhere, in a cloud of pristine hydrogen and helium in the deep past, atoms falling toward each other and falling until the pressure and the temperature reached the threshold, and a star was born. No one was there to see it. Nothing was there to see it. But it happened. It happened, and the light from it crossed a dark universe, and eventually, it ionized the hydrogen in its neighborhood and began the long work of lighting the cosmos back up. And everything you can see on a clear night is downstream of that moment. Every star you have ever looked at owes something to those first, nameless, unobserved population 3 stars that burned in the dark and made the elements and died, and gave the next generation something to work with, and the next generation gave the generation after that something richer still, and so on for billions of years, enriching the gas and the clouds and the regions where new stars would form, building up the periodic table one stellar generation at a time. Your body is the output of that process, not metaphorically, not poetically, chemically, physically, measurably. The atoms you are made of have been through stars. Most of them have been through more than one. They arrived in the cloud that would become our solar system, already bearing the marks of stellar processing, already carrying within them the record of lives that were lived and fires that burned before our star existed. And our star, the Sun, came late. The universe was, by the time our Sun formed, already 9 billion years old, already 2/3 of its current age. The cosmos had been building stars and galaxies and enriching its gas for 9 billion years before the particular cloud of gas and dust that would become our solar system finally pulled itself together and collapsed and lit. But we're getting ahead of ourselves just slightly. That part, the Sun's late arrival, the cosmic noon that peaked before our Sun, was even a thought. The present moment and what it means comes next. Let's keep moving forward through the timeline, step by careful step, unhurried. The cosmic dawn has broken, the first stars have blazed and died, the first galaxies are forming, pulling themselves together in the dark matter scaffolding, growing and merging and building up. The universe is, by about 1 billion years in, beginning to look like something that would be recognizable, at least in broad structure, as related to the universe we live in today. Not identical, not nearly as evolved, but recognizably in the business of making stars and organizing matter. And it is going to keep getting busier. The rate of star formation is going to climb. More and more gas enriched by more and more stellar deaths is going to funnel into more and more newborn stars. The universe is ramping up towards something, a peak, a maximum rate of star-making, a cosmic high point when the universe is producing new stars faster than it ever has or ever will again. That peak is coming, and when it arrives, well, it turns out it arrived a long time ago. We'll get there. Let's keep following the story forward through the dark, through the dawn, through the growing light of a cosmos that is, for now, still building toward its brightness. The gas that the first supernovae scattered, that carbon and oxygen and silicon and iron, is not sitting still. It's mixing back into the surrounding gas clouds, being swept up in shock waves from other supernovae, cycling through the interstellar medium of the young galaxies that are forming. And those galaxies are themselves pulling in more gas, cold streams of fresh hydrogen from the cosmic web, the filaments of the large-scale structure funneling material in toward the galaxy centers. The rate of star formation is climbing. Think of it this way. In the very earliest time, the first hundreds of millions of years, there were some stars, those enormous population 3 pioneers. But the machinery of star formation was still getting going. There wasn't much enriched gas yet. There weren't many galaxies. There weren't many places and many conditions favorable to the formation of large numbers of stars. The universe, in its cosmic dawn, was just starting to warm up. Over the next few billion years, it kept warming up. More galaxies, more enriched gas, more star-forming regions, more supernovae scattering more enrichment into more clouds. The rate of new star formation rising, filling the universe with more light each billion years, more color, more complexity. Galaxies growing, merging, building themselves up into the large structures we see today. The great machinery of the cosmos running at higher and higher capacity. And this is where we are heading as the story moves into its next chapter. Toward the brightness, toward the cosmic noon, toward the moment when the universe, by any measure that counts new stars being born, was at its most alive, at its most productive, at its most brilliantly, furiously creative. And when we get there, when we stand at cosmic noon and look around at the universe at its peak of starlight and new stars and furious galactic activity, and then look at the clock and realize where we are in the story, where the Earth is, where the Sun is, where we are, that's when the real surprise lands. But we're not quite there yet. Let's stay with the early universe a moment longer, in that first billion years, in that extraordinary transition from the long dark to the cosmic dawn, and appreciate what was accomplished in that time. In a universe only a billion years old, which is cosmically speaking very young, the first stars had already lived and died. The first heavy elements had already been forged and scattered. The first galaxies were already building themselves up. The universe, which had spent its first 380,000 years as a sealed, hot, opaque fog, and then its next 100 million or more years as a cool, dark, silent gas, was, by a billion years in, already something astonishing, already lit, already structured, already chemically complex enough in some regions to contain the ingredients for planets. Not our planet. Not yet. Not for another 8 billion years or so, but the ingredients were there, beginning to spread. The universe was, in the truest sense, getting ready. And you and I are, in the truest sense, the downstream products of that readiness, of all those early stars and supernovae and enrichment cycles and galaxy collisions and cold gas streams and shock waves and convection zones and fusion reactions. Every step of it necessary. Every step adding something, another element, another enriched region, another generation of stars slightly better equipped to forge the materials that would eventually, in a particular solar system, around a particular star, in a particular arm of a particular galaxy, end up in rocks and oceans and living cells and, after a few billion years more, in minds lying quietly in the dark, wondering where they came from. The answer, as best we can tell, is from all of this. From the fog that cleared 380,000 years in, from the dark that followed, from the first enormous stars that blazed into being in that dark and gave the universe its first heavy atoms, from the supernovae that scattered those atoms into the gas, from the second and third generations of stars that formed from that enriched gas and repeated the process, building the periodic table up and up and up until there was enough of everything to make something as complicated as you. You are, in the most literal sense we know how to measure, a product of the cosmic dawn, made in the stars, scattered in supernovae, assembled over billions of years into the extraordinary organization of matter and chemistry and biology that is right now listening to this somewhere in the dark, wondering about it, and there's something in that, something worth carrying gently into sleep. The universe turned its lights on in the dark for the first time, more than 13 billion years ago, and some of the atoms that were forged in those first fires are in you right now. Let's follow the story forward from there, into the universe's long, bright morning, toward the noon it has already passed, and then into the long, slow afternoon that stretches ahead of it, and us, for longer than any of us can really hold in mind at once. But we'll take it slowly, there's no rush, the universe has time, and so do you. And so here we are, some 13.5 billion years into the story, standing, in the grand scheme of things, at what feels like a fairly late hour. The Big Bang is ancient history. The first stars have come and gone. The universe has been through its infancy, its dark childhood, its bright and fiery adolescence. It feels, from the inside, like we've arrived at something mature, settled, something whose great events are already in the past. But that feeling, it turns out, is almost perfectly backwards. We'll come back to that. We'll come back to it in detail, and I think when we do, you may find it genuinely startling. For now, let's follow the thread forward from where we left it, from the cosmic dawn, from the first stars and the first scattered heavy atoms and the slow assembling of galaxies, and move into the universe's long, complicated morning, because something interesting was already happening, something that astronomers in the 21st century are still, in a very real sense, scrambling to understand. We have a telescope now, you may have heard of it, called the James Webb Space Telescope, JWST for short. It was launched on Christmas Day 2021 after decades of development, and it sees the universe in infrared light, which means it can see things that visible light telescopes cannot. Specifically, it can see very distant, very ancient things, objects so far away that the expansion of the universe has stretched their light into the infrared part of the spectrum, well past what human eyes or ordinary cameras could detect. And because light travels at a fixed speed, looking far away means looking far back in time. The further out JWST peers, the further back in time it's seeing. What it found when it started sending images back was not entirely what people expected. The models we had, the beautiful, carefully built models of how galaxies form and grow, predicted a certain kind of early universe. They predicted that in the first few 100 million years after the Big Bang, galaxies would be small and rough and chaotic, building themselves up slowly from smaller pieces, clumping and merging over vast stretches of time into the larger, more organized structures we see today. A bottom-up process, patient and gradual. The big things come later, and in broad strokes, that picture is still correct. But JWST has been finding things that don't quite fit neatly inside it. It has found galaxies, real, massive, surprisingly well-formed galaxies, existing only about 300 to 500 million years after the Big Bang. That sounds like a long time, but set it against the universe's full 13.8 billion years, and it's astonishingly early. If the universe's entire current age were 1 calendar year, 300 million years would be the first 8 days. The universe was barely out of its cradle, and already there were galaxies more massive than our models predicted should have had time to form. Some of these early galaxies contain stars in numbers that challenge the math. To build up that much stellar mass that quickly, they would have needed to form stars at rates far higher than the models suggested was possible so soon. There is real, ongoing scientific discussion about what this means, whether the models need adjustment, whether our understanding of early star formation is incomplete, whether there are physical processes we haven't fully accounted for. Nobody is saying the models are entirely wrong, but the data from JWST is genuine, and it is pushing the field in new directions. This is what science looks like from the inside, not from the textbook. It's not a smooth, settled story. It's a working picture, under active revision, and some of the most interesting revisions are happening right now, in real time, as the data comes in from a telescope orbiting 1.5 million kilometers from Earth. We live at an unusual moment in that respect. We happen to be the first civilization, as far as we know, that has had a tool capable of seeing the universe's first few hundred million years directly. Everything we know about cosmic dawn and the very first galaxies has arrived within the span of a few years. We are still, in a genuine sense, reading the earliest chapters of the story for the first time. And what those chapters seem to be telling us is that the universe was productive, startlingly, perhaps uncomfortably productive, very early. Galaxies forming fast, stars igniting in the dark, structure pulling itself together out of the fluctuations in the primordial gas with an urgency the models hadn't fully captured. That urgency, that early burst of productivity, connects to something I want to linger on for a moment, because it sets up the strangest and most important fact in this whole long story, the fact that is, in some sense, the whole reason we are telling it this way. The universe has a peak, a moment, or rather, an era, at which the business of making new stars was happening at the greatest rate it ever has or ever will. A cosmic noon, if you like. And that noon has already passed. It passed roughly 10 to 11 billion years ago. The technical way to say this is that star formation peaked at a redshift of approximately z equals 2. Redshift is how astronomers measure distance and look back time in an expanding universe. The higher the redshift value, the further away something is, the further back in time we're seeing it, and the more the universe's expansion has stretched its light. A redshift of 2 corresponds to a point when the universe was roughly 3 to 4 billion years old. The universe, in other words, was in its early youth, not yet even a third of its current age, and it was already at the height of its creative power. At cosmic noon, new stars were forming across the universe at a rate roughly 10 times higher than they are today. 10 times, the universe was ablaze with formation. Gas was collapsing into stellar nurseries at a frenzied pace. Galaxies were crashing into each other and triggering enormous bursts of new star birth. It was, in the truest sense, the most luminous era the universe has ever known or will know. And then it declined. Slowly at first, then more steadily. Over the billions of years since that peak, the rate of star formation across the observable universe has been falling. Gas gets used up. Galaxies mature. The raw material for new stars, cold, dense hydrogen gas, becomes less abundant in the right places and the right conditions. The universe's great productive era was already winding down before our sun was even a thought. By the time we're here, now, 13.8 billion years into the story, the rate of star formation across the universe is perhaps 1/10 of what it was at cosmic noon. 1/10. The stars we see in our night sky and all the stars in all the galaxies telescopes can show us represent the output of a universe already past its prime, not dramatically past it. The fires are still burning, still making new stars, still extraordinary by any ordinary measure. But the peak is behind us. Think about what that means. The question most people carry into a video like this one is some version of how did we get here, what came before, and the implicit assumption is that here, now, is the destination, the culmination, the grand arrival. But the universe's own account book suggests otherwise. By the measure of how fast it is making new stars, the universe peaked before the sun was born, before the earth formed, before the first bacteria appeared in the oceans of a young world, before any of it. The universe's most productive era, the era in which it was most vigorously and rapidly building the structures that define it, was a long time ago. We are not the culmination, we are the late morning, or perhaps the early afternoon. There's a certain vertigo to that if you let it settle, but there's also something else in it. Something that I find, oddly, rather peaceful. We are not latecomers to a finished cosmos, we are early. The universe still has extraordinary things ahead of it. We are just watching from a particular window, a bright one, a warm one, fortunate in its timing, before the long, slow afternoon begins. But let's stay in the present for a little while longer before we move toward what comes next. Because the present has its own strangeness, and it deserves a proper look. What is the universe right now made of? Not in terms of its history, in terms of its content. What fills it today as of the moment you're listening to this? The honest answer is that most of it is something we cannot identify. We have a word for it, 2 words actually, but the words are placeholders for genuine, deep ignorance. And I think it's important to say that plainly. Here is what we know. Everything you have ever seen or touched or thought about, every planet and star and galaxy, every rock and tree and person, every atom of hydrogen and carbon and iron and oxygen, all of that is made of ordinary matter. Baryonic matter in the technical language, named for the family of particles that includes protons and neutrons. And when astronomers add it all up, all the ordinary matter in the observable universe, they find that it accounts for roughly 5% of the universe's total energy content. 5%. The rest is divided between 2 things we do not understand. About 27% of the universe appears to be dark matter. Not dark in a poetic sense. Dark in the literal sense that it does not emit light, does not absorb light, does not interact with light at all. We cannot see it. We cannot detect it directly with any instrument we currently have. We know it is there because of its gravitational effects. The way galaxies rotate, the way light bends around clusters of galaxies, the way structure formed in the early universe in a pattern that only makes sense if there is far more gravitating material than the visible stars and gas can account for. Dark matter is, as best we can tell, real. It played a crucial role in building the structure of the universe we see. But what it actually is, or what particle or particles it consists of, whether it is something entirely outside our current catalogue of known physics, remains, as of now, genuinely unknown. And then there is dark energy. Dark energy is the name we give to whatever is driving the expansion of the universe to speed up, and it accounts for roughly 68% of the universe's total energy content. More than 2/3 of everything in terms of energy is something we have given a name to but do not, in any deep sense, understand. That 68% brings me to something that needs a moment of its own, because the story of dark energy is a story about a surprise, a very large surprise of the kind that only comes along a few times in a generation of science. It begins with a question that seems simple on the surface. The universe is expanding. Edwin Hubble established that in the 1920s, and it has been a cornerstone of cosmology ever since. But the question astronomers were grappling with through the late 20th century was, what is expansion doing over time? Is it slowing down as you might expect? Gravity, after all, acts as a brake. All the matter in the universe is pulling on all the other matter. The natural expectation for decades was that the expansion was decelerating, slowly braking, the way a ball thrown upward slows as gravity pulls it back. The question was only whether there was enough matter to eventually reverse the expansion entirely and pull everything back together, or whether it would coast outward forever, slowing but never stopping. Nobody, or almost nobody, was expecting the third option. In 1998, two independent teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, were using a particular kind of stellar explosion called a Type Ia supernova as a cosmic measuring tool. Type Ia supernovae are useful because they all explode with roughly the same intrinsic brightness, which means that by measuring how bright they appear in the sky, you can calculate how far away they are. And by measuring the redshift of the galaxy they exploded in, you can know how fast that galaxy is moving away from us. What both teams found when they analyzed their data in 1998 was not a universe slowing down, it was a universe speeding up. The distant supernovae were dimmer than they should have been if the expansion were decelerating. Dimmer means farther away. Farther away, for a given redshift, means the universe was expanding more slowly in the past and is expanding faster now. The expansion is accelerating. Both teams independently found the same thing, and both teams spent a considerable amount of time checking their data, questioning their instruments, and looking for errors because the result was so unexpected. But it held up, and in 2011, Perlmutter, Schmidt, and Rees were awarded the Nobel Prize in Physics for the discovery. Something is pushing space apart, something that behaves in its effects like a repulsive energy built into the fabric of space itself, present everywhere, constant in its density even as space expands and apparently growing in its total effect as the volume of the universe grows. We call it dark energy. It may be related to what Einstein called the cosmological constant, a term he introduced, then famously discarded, in his field equations for general relativity. It may be something else entirely. As of right now, we genuinely do not know what it is, but its implications are vast, and we will come back to them when we talk about the universe's long future. For now, the important thing to hold is simply this. The universe is not only still expanding, but expanding faster and faster. Whatever end waits for it at the far end of time, it is not a collapse. It is a spreading, a thinning, a gradual and accelerating recession of everything from everything else. Let the room around you feel briefly strange. Whatever dark energy is, it is here too, in the space between you and the nearest wall, in the space between the atoms in your hand. It is everywhere, constant, and it is winning over gravity at the very largest scales. The universe is being pulled apart by something we cannot see and cannot name, and has been for billions of years. That is the present. Mysterious and strange and ongoing. Now let's find ourselves in it more precisely. Where are we in this picture? Not philosophically, literally. When did our particular patch of the universe come into being? When did the star at the center of our solar system first switch on? The Sun formed approximately 4.6 billion years ago. From a cloud of gas and dust in a spiral arm of the Milky Way, gravity pulled material inward until the pressure and temperature at the center became high enough to ignite hydrogen fusion, and a new star was born. Our star, the one whose light warms your face and powers every green thing on the surface of this world. But here's the thing to sit with for a moment. 4.6 billion years ago, the universe was already 9 billion years old. 9. The universe had been around. Stars had been forming and dying. Galaxies had been evolving. Supernovae had been scattering heavy elements into the interstellar gas for 9 billion years before our Sun existed. Cosmic noon, the peak of star formation, had already come and gone. The universe was past its most productive era. It had already lived more than 2/3 of its current age. Our Sun is not an early star. It is not a first-generation star. It is not even a second-generation star in all likelihood. The gas from which it formed had been through stellar cycles, through supernovae, through the enrichment process more than once. Our Sun is made of material that has been processed by earlier generations of stars and returned to the interstellar medium to be gathered up again. It is, in a word, experienced material. Old stardust, reassembled, and so are you. The iron in your blood was forged in the core of a massive star that died in a supernova explosion, possibly more than one. The oxygen you are breathing was made in stellar fusion, the calcium in your bones. The carbon at the heart of every biological molecule in your body. All of it was made somewhere inside a star, sometimes multiple generations of stars, scattered into space by their deaths, collected into clouds, collapsed into a new solar system, incorporated into a planet, and eventually organized, over billions of years of chemistry and geology and biology, into the particular arrangement of atoms that is you right now, lying somewhere in the dark, listening to this. You are recycled stardust, not metaphorically, not poetically, in some vague, inspirational sense, chemically, measurably, literally. The atoms in you have histories. They have been in other places. They have been part of other things. And when you are eventually done with them, they will go on to be part of other things still. That is not a comforting fiction. It is what the nuclear physics and the stellar evolution models and the elemental abundances all confirm. Carl Sagan said we are made of star stuff, and it is one of those statements that sounds like poetry, but is simply true. The Earth formed shortly after the Sun, about 4.5 billion years ago. From the leftover disk of gas and dust that didn't end up in the Sun, smaller bodies clumped together, and one of them, through a long, violent, chaotic process of accretion and collision, became our world. By the time the Earth was a few 100 million years old, something had happened in its oceans, or near hydrothermal vents, or in some warm, shallow pool. The exact setting is still debated. That marks one of the most improbable and extraordinary events in the known history of the universe. Chemistry became biology. Self-replicating molecules appeared. Life, by whatever mechanism and in whatever setting, began. But the point I want to make here is about scale and timing, a whole story. The Sun, the Earth, life, evolution, civilizations, everything began in the last third of the universe's current age. We formed in what you might call the late morning of the universe's present era. Not the beginning, not anywhere near cosmic noon, the late morning of a long day, and even that puts us earlier than it might feel from the inside. Now the universe, as we have discussed, is not sitting still around us, it is changing, and some of those changes are happening on timescales that are short enough, in cosmic terms, to be genuinely interesting to think about. Not during your lifetime, or your children's, or your species' lifetime, most likely, but soon, in the way that cosmologists use that word. The nearest large galaxy to our own Milky Way is Andromeda. Its formal designation is Messier 31 or M31. If you are in a dark enough place away from city lights, you can actually see it with the naked eye. A faint, smudged patch of light in the constellation Andromeda, unremarkable to look at, easy to overlook. It doesn't look impressive from here, it doesn't look dangerous, it looks like a small, soft smear of fog. But Andromeda is a galaxy of roughly 1 trillion stars, roughly twice as massive as the Milky Way, and it is coming toward us, directly toward us, at approximately 110 kilometers per second. 110 kilometers per second sounds fast. And it is fast, faster than anything you will ever encounter in daily life, faster than any spacecraft humanity has built, fast enough to travel from here to the moon in about an hour. But by cosmic standards, and given the distance involved, what is about 2.5 million light-years currently separates the Milky Way from Andromeda, 110 kilometers per second is actually a slow, steady, patient approach. Not a dramatic rush, a gradual, inevitable closing of a vast gap. In approximately 4 to 4.5 billion years, the Milky Way and Andromeda will begin to merge. The word merge is important. Collide is the word that tends to get used in pop science descriptions, and it isn't wrong exactly, but it conjures images of two solid objects smashing into each other, which is misleading. Galaxies are mostly empty space. The stars in the Milky Way are separated from each other by enormous distances. The nearest star to our Sun, Proxima Centauri, is about 4 light-years away. When two galaxies merge, the stars typically pass by each other without directly hitting, like two swarms of bees interpenetrating. The collision is gravitational, not physical. The galaxy's mutual gravity distorts them, pulls long trails of stars out into space, draws them together, pushes them apart, and draws them back again in a long, drawn-out gravitational dance that takes hundreds of millions of years to play out. The gas clouds in both galaxies, however, do interact, and those interactions compress the gas, triggering new bursts of star formation. A galactic merger is, paradoxically, a period of intense creativity, great waves of new stars igniting from the disrupted gas. What emerges from a merger like this, after the gravitational dynamics have settled, is typically no longer a spiral galaxy. Spirals, with their beautiful organized arms, are the signature of rotation and relative youth and ongoing star formation. When two spirals merge, the result tends to be an elliptical galaxy, a large, rounded, less structured cloud of stars, red and gold in color because the brilliant blue-white young stars have mostly burned out, and what remains are the longer-lived, cooler, older ones. A galaxy past its most creative phase. Beautiful in its own way, but quieter. The merged Milky Way and Andromeda, sometimes given the informal name Milkomeda, though that is not an official designation, will be something like this. A large elliptical galaxy containing the descendants of both our galactic families, orbiting a common center. The Sun, in all likelihood, will still exist when this begins. It will be old and somewhat brighter than it is now. We'll talk about what that means for us in a little while. But it will still be burning. Whatever is on Earth at that point, if anything is, would look up at a sky being slowly, dramatically transformed. Two galaxies in the process of merging look extraordinary. Long tidal streams of stars arcing across the sky, the center of the other galaxy approaching, brightening, changing the look of the night. It would be among the most spectacular views available anywhere in the observable universe during that era. Our descendants, if we have any, 4 billion years from now, would live inside one of the most dramatic events in the Milky Way's entire history. But let's linger for a moment on where we are before moving forward. Because the present moment, this particular morning in the universe's long day, is actually a rather special one, even if its specialness is easy to miss. We happen to live at the right time to see other galaxies. That sounds like a small thing, but it matters more than it seems. The universe is expanding, and the further away a galaxy is, the faster it is receding from us, because space itself is expanding everywhere simultaneously. There is a distance beyond which galaxies are receding faster than the speed of light, not because they are moving through space at that speed, which would violate relativity, but because the space between us is growing so quickly. Light from those galaxies can never reach us. They are beyond our cosmological horizon. Right now, we can see thousands of billions of galaxies within our observable universe. We have the Hubble Space Telescope's deep field images showing thousands of galaxies in a patch of sky no bigger than a grain of sand held at arm's length. We have JWST going deeper still. We have a universe richly populated with observable structure. But because the expansion is accelerating, because dark energy is pushing everything apart faster and faster, the number of galaxies we can see will decrease over time. Galaxies in our local group, the small family of galaxies to which the Milky Way and Andromeda belong, will remain accessible. Gravity within the local group is strong enough to hold the group together against the expansion. But galaxies outside the local group are receding and accelerating in their recession, and over very long timescales, they will eventually redshift so far that their light becomes undetectable. They will effectively vanish from our sky. Someone, or something, observing the universe from the Milky galaxy hundreds of billions of years from now would look out and see only a small handful of companion galaxies in a vast, otherwise empty dark. They would have no direct observational evidence that any other galaxies exist. The evidence of the Big Bang itself, the cosmic microwave background, would have redshifted beyond detection. If they were trying to do cosmology the way we do it, using the large-scale structure of the universe as their data, they would find themselves in a cosmos that looks, from their perspective, static and alone. They would not know what we know. They would not be able to know it from observation alone. They would have inherited a universe in which the information needed to reconstruct the full story was simply no longer present in the sky. We are living right now in the era in which the full richness of the universe is visible. We can see the cosmic microwave background. We can see galaxies at high redshift, galaxies as they were billions of years ago. We can see the structure that dark matter built. We have right now the most complete possible observational picture of the cosmos that any civilization in this galaxy will ever have. That's a strange thing to hold. We tend to think of progress as cumulative, as always moving toward more. But in cosmology, the universe itself is slowly withdrawing its evidence. Future civilizations, if they exist, will look out at a simpler, lonelier-looking sky and have no way to know what was once there. In that sense, we are not too early. We are, in fact, at something close to the optimal moment to do cosmology. The evidence is all still here. The story is still readable. And we have learned to read quite a lot of it. We know that our universe is 13.8 billion years old, measured from the cosmic microwave background by the Planck satellite with extraordinary precision. We know it began in a state of extraordinary density and temperature. We know it expanded and cooled. We know it forged its first nuclei in the first 20 minutes, and its first atoms 380,000 years in. We know it spent its first 100 million years or more in darkness. We know the first stars ignited and began the long process of seeding the universe with heavy elements. We know galaxies formed and grew and merged and evolved. We know star formation peaked roughly 10 to 11 billion years ago and has been declining since. We know the Sun formed 4.6 billion years ago from material that was already the product of multiple stellar generations. We know the expansion is accelerating, driven by something we call dark energy and do not understand. We know quite a lot. And we know at the same time that some of the most important questions, what dark energy is, what dark matter is, how the matter-antimatter asymmetry came to be, exactly how the first galaxies formed so quickly, remain genuinely, honestly open. The universe is not yet fully read. It is a book we are still partway through, and some of the most interesting chapters are still being turned. But here is the thing I want you to carry forward into the next part of this story. The thing that changes how the whole picture looks once you really sit with it. We are at 13.8 billion years. Star formation peaked 10 to 11 billion years ago. The universe is, by that measure, already past its most creative era. Already in decline in the specific sense that it is making fewer new stars than it was at its height. And yet we are still relatively early. We are early in a much longer story. The universe has not finished being interesting. It has not finished being eventful. It has only finished being young, and the transition from young to old, from bright morning to long afternoon, from the era of light to the era of something else entirely. That transition is still ahead of us. Most of it is still ahead of us, in a sense we haven't yet fully reckoned with. If you've been drifting a little, that's perfectly fine. The ideas will still be here. But if you're still with me, let yourself settle a little deeper into wherever you are, in the bed, or the dark room, or wherever the sound of this has carried you. Because what comes next is where the story gets really strange. The universe's future is, in some ways, more mind-bending than its past, because its past was at least eventful. What its future holds is a kind of grandeur that has almost nothing to do with the kind of events we think of when we think of cosmic history. But let's not get ahead of ourselves. We're still in the present. We're still in the era of stars, of galaxies, of light. The fires are still burning. The Milky Way is still making new stars, slowly in its spiral arms. The sun is still in the middle of its life, burning hydrogen steadily in its core, as it has been for 4.5 billion years and will continue to do for roughly another 5 billion. And around that sun, a small blue world turns in the dark, thin-skinned, warm, improbably suited to the particular chemistry of life. A world that has hosted living things for most of its history and thinking things for a very recent, very brief fraction of it. Where in the world are you listening from tonight? Whatever corner of that small world you occupy, whatever room, whatever city, whatever particular patch of a particular continent, you are on a piece of second or third generation stardust, orbiting a middle-aged star inside a galaxy that is still making stars but doing so less vigorously than it was billions of years before you were born, in a universe whose expansion is accelerating under the influence of something nobody can name, 13.8 billion years into a story that is, by any fair measure, still near its beginning. That is where you are. That is when you are. And the fact that you are here at all, asking these questions, listening to this, so that is in its own way one of the most extraordinary things the universe has produced in its first 13.8 billion years. Not because there is anything cosmically special about humanity in the grand scale of things, but because the universe has spent all of that time, all of that vast and improbable machinery of stars and supernovae and galaxies and chemistry and biology, arriving at matter that wonders about itself, matter that lies in the dark and asks where it came from. That is new, or at least as far as we know, it is rare. And it is happening right now in this era, in this bright, brief window of the universe's long life. There is something in that worth holding gently. We'll come to the long future soon, to the slow cooling, to the fading of the fires, to the deep darkness that stretches ahead for timescales that make the age of the universe so far seem like nothing at all. But that is the next chapter. For now, let the present be what it is. An unlikely warmth. A brief and brilliant morning. We are not at the end of anything. We are, in the truest sense, still quite near the beginning. And yet, the morning does not last forever. We have been moving slowly through this story, through the first fraction of a second, through the dark ages through the birth of the first stars, through the long noon of the cosmos when galaxies blazed and the universe hummed with the making of new suns. We have arrived gently at the present. At you, lying there, the atoms of your body forged in stellar cores, the light in your room a pale echo of processes that began long before the sun existed. But the story does not end here, it continues. And the part that continues is vast, incomprehensibly, almost insultingly vast. Compared to what is coming, the 13.8 billion years behind us is barely a preface, a clearing of the throat before the real silence begins. So let's go forward, slowly. There's no hurry, the night is long. Let's start with something close. Something that sounds far away, but is, on cosmic time scales, right around the corner. The sun is brightening, not quickly, not noticeably from one human lifetime to the next, or from one century to the next, but steadily over geological time. The sun puts out slightly more energy than it did before. It has been doing this since it formed, and it will keep doing it. Stars like the sun grow gradually more luminous as they age, because as hydrogen fuses into helium in the core slowly contracts and heats, and a hotter core means a brighter star. It is the quiet, slow physics of stellar aging running in the background, invisible on any human time scale. The number is roughly 10% brighter per billion years. That sounds modest, and in some ways, measured against the vast changes still to come, it is modest. But 10% more energy arriving at Earth every billion years adds up. It adds up to something that, when you sit with it, is rather striking. In about 1 billion years from now, not 5 billion, not 10 billion, 1 billion, which is less time into the future than the time that separates us from the first animals with hard shells, the sun will be bright enough that Earth's surface temperatures will have risen considerably. The models suggest that in roughly that time frame, the increased solar energy will begin to drive a runaway effect on the planet's water cycle. The oceans will warm. More water will evaporate into the atmosphere. Water vapor is itself a greenhouse gas, so the warming accelerates. And at some point along that trajectory, the exact timing is genuinely uncertain because Earth's climate system is complex and will respond in ways we can only model approximately. The oceans will begin to boil away in earnest. The water, which has been here for billions of years, which carved the canyons and filled the seas and made life possible, will escape to space. Earth, in about 1 billion years, becomes uninhabitable for life as we know it. Not because the sun has died. The sun will not die for another 4 billion years after that. But life's window here does not extend to the sun's death. It is already closing. Slowly, yes, 1 billion years is a long time, longer than the history of complex animal life on this planet. But it is closing. We do not live at the culmination of the Earth's story. We live somewhere in its middle chapter. Perhaps a little past the middle, if we measure by the window available to life. The oceans that lap at every shore tonight, the ones you can picture right now if you close your eyes, or perhaps you're near one, perhaps you can hear it, they are temporary. Everything is temporary. It is just that the time scales vary. This is not cause for despair. It is just the calendar of a planet, and the planet itself will persist even after the oceans are gone. Stripped, desiccated, bare rock baking under a brightening star, but still there, still orbiting. For another few billion years after the last drop of liquid water has left. Then the sun changes. About 5 billion years from now, the sun will exhaust the hydrogen in its core, not in its whole volume. There will be plenty of hydrogen left in its outer layers, but in the core, where the fusion happens, the fuel runs low. the core begins to contract under its own gravity, heating up further. And that extra heat ignites a shell of hydrogen around the contracting core, a ring of fusion that burns more fiercely than the core ever did. The energy from that shell pours outward, and the outer layers of the sun respond. They expand. The sun grows. It grows slowly at first, then faster. Over millions of years it balloons outward, its surface cooling as it spreads, its color shifting from yellow-white toward orange and then red. It becomes what astronomers call a red giant, a swollen, enormous, cooler-surfaced star that fills a far greater volume of space than before. In that phase, the sun will have expanded to perhaps 100 times its current diameter. And the orbit of Earth, assuming Earth is still there, which is genuinely uncertain because tidal forces and the expanding atmosphere of the dying star complicate things considerably, will be at best a scorched and airless cinder in the outer reaches of what used to be the sun's surface. Some models suggest the expanding sun may actually engulf the Earth's orbit. Others suggest Earth might drift outward slightly as the sun loses mass. The honest answer is we don't know exactly, but either way, the Earth as a living world is long past its end by then. Mercury will certainly be swallowed. Venus too, most likely. The inner solar system will be absorbed into the dying star's body. And then the sun, having exhausted even that fuel, will shed its outer layers in a slow, expanding shell of gas called a planetary nebula. A beautiful irony, since planetary nebulae have nothing to do with planets. The name is just a historical accident because early astronomers thought the glowing rings looked a bit like the disks of planets through their small telescopes. The shed gas will drift outward into space, enriched with the carbon and nitrogen and oxygen that the sun's core processed during its life. It will become part of the interstellar medium. Perhaps billions of years later, part of it will be incorporated into another star, another planet. What remains at the center will be the sun's core, compressed, spent, no longer fusing. A ball of carbon and oxygen roughly the size of the Earth, no longer supported by fusion pressure, held up only by the quantum mechanical stubbornness of tightly packed electrons. We call it a white dwarf. The sun will end as a white dwarf. White dwarfs are strange objects. They are extraordinarily dense. A teaspoon of white dwarf material would weigh roughly 5.5 tons here on Earth. They are extremely hot when they first form, white hot from the energy of gravitational collapse, and they glow brilliantly for a time. But they have no fuel, they are not fusing anything, they are simply radiating the heat they were born with slowly into the surrounding space. And they cool. Over billions and billions of years, timescales longer than the current age of the universe, a white dwarf fades. It dims from white to yellow to orange to red to infrared. Eventually, in theory, it cools to the temperature of the surrounding space and becomes what cosmologists call a black dwarf. A cold, dark, inert lump of compressed carbon and oxygen drifting silently through the galaxy. No black dwarf is thought to exist yet. The universe is not old enough. The cooling process takes longer than 13.8 billion years. The oldest white dwarfs in our galaxy are still radiating, still dimly glowing. The black dwarfs are a phenomenon of the very deep future, but they are coming, and here is where the story begins to open into something much larger, because we have been talking about the sun as though it is a special case. It is special to us, but it is one of a few 100 billion stars in the Milky Way alone, and the Milky Way is one of hundreds of billions of galaxies in the observable universe. Every one of those stars has a lifespan. Every one of them will end in a white dwarf, or a neutron star, or a black hole, depending on how massive they are. And new stars are being born to replace them, yes. But as we said in the last chapter, the rate of star formation has been falling for 10 billion years. The universe is past its peak of making new ones. The fires are banking, slowly, steadily, over timescales so long they are hard to hold in the mind. The universe is running down. Let's think about what happens to the wider structure of things. Right now, if you were to stand outside on a clear night far from city lights, you would see thousands of stars scattered across the sky. You would see the faint smear of the Milky Way's own disk. And if you had a good telescope and knew where to look, you would see other galaxies, faint smudges of light, entire islands of stars, some of them tens of millions or hundreds of millions of light years away. The universe, from your vantage point, is full of other galaxies. That will not always be true. The universe's expansion is accelerating. We talked about that discovery, 1998. Two teams, the supernovae that were dimmer than expected because they were farther away than they should have been. The shock of realizing that the expansion of space was not slowing under gravity, but speeding up under the influence of something we call dark energy. That acceleration has a profound long-term consequence. As the universe expands faster and faster, galaxies beyond our local neighborhood are receding from us ever more quickly. There is a distance, not a fixed wall, but a dynamical boundary, beyond which galaxies are moving away faster than light can cross the growing gap between us and them. We cannot, even in principle, receive any more light from them. They are beyond our cosmic horizon. Right now, that horizon includes an enormous number of galaxies. The observable universe contains roughly 2 trillion galaxies by some estimates, though many of them are too faint and distant for us to resolve clearly, even with our best instruments. But in the future, as the accelerating expansion continues, more and more of those galaxies will cross beyond our horizon. Their light will redshift. It will stretch to longer and longer wavelengths, growing dimmer and dimmer, and eventually it will be undetectable. The galaxies will, for all practical purposes, vanish from the observable sky. In perhaps 100 billion years, roughly 7 times the current age of the universe, all galaxies beyond the local group will have receded beyond our horizon. The local group is the small cluster of galaxies that includes the Milky Way and Andromeda, and a few dozen smaller companions. Everything outside it will be, effectively, gone. Not destroyed, just unreachable, invisible, carried over the horizon by the expansion of space itself. Future astronomers, if there are any, will look out at the sky and see only their own galaxy, perhaps the merged remnant of the Milky Way and Andromeda, the entity sometimes called Milkomeda. And beyond it, nothing, or nothing detectable. The universe will appear to any observer within the local group to be a single island galaxy surrounded by a vast, empty, dark expanse. And here is the haunting part. The cosmic microwave background, that faint afterglow of the Big Bang that was our strongest evidence for how the universe began, will by then have redshifted so far that it is entirely undetectable. The temperature of the background radiation will have dropped so low, the wavelengths stretched so long that no instrument could measure it. The very evidence of the Big Bang will have faded from the observable universe. Future cosmologists in that era, if they exist, will have no way to discover what we know. The universe's own expansion will have erased the record. They will see a static, apparently eternal, single galaxy in a dark void. They might reasonably conclude that this is all there is and all there has ever been. They will be wrong, but they will have no way to know it. The evidence will be gone. We are fortunate, in a strange way, to live in this early era. We can still see the whole story written in the sky. Now, the local group consolidates. The stars continue to burn. And this is where we enter the longest named chapter in the far future, the Stelliferous Era. Stelliferous means star-bearing. The era of stars, the period of cosmic history in which ordinary stars, fusion-powered self-luminous suns, shine in the night. We live in the Stelliferous Era right now. We have always lived in it. It began with the first population 3 stars, those enormous blue giants that lit up the cosmic dawn somewhere around 100 to 200 million years after the Big Bang.
And it will continue, according to current cosmological models, for an extraordinary length of time, roughly 100 trillion years. 100 trillion. Let me stay with that for a moment.
The current age of the universe is 13.8 billion years. 100 trillion years is about 7,000 times that. If you started a clock at the moment the first stars ignited and let it run until the last star goes dark, the moment we are living in right now, 13.8 billion years in, is less than 100th of the way through the stellar era. We are on the stelliferous timeline in the very first chapter, perhaps the first page. The stars burning in the sky tonight are mostly near the beginning of their lives, or at worst, their middle. The red dwarf stars, the small, cool, dim stars that are actually by far the most common type in the galaxy, burn so slowly and so frugally that they can live for trillions of years. A red dwarf with about 1/10 the mass of the Sun can sip its hydrogen fuel for 10 trillion years or more before it finally fades. There are stars in our galaxy right now that will still be burning when the current age of the universe seems like a brief prologue. The stars will not go out quickly. This is not a sudden darkness. It is a slow dimming spread over timescales almost beyond comprehension. As one by one the stars use up their fuel, and the rate of new star formation, already in decline, dwindles further and eventually stops. The last stars will be those small red dwarfs burning low and dim and red in the darkness of what will by then be a very different universe. And then they too will exhaust their hydrogen and collapse, not to explode as supernovae, as massive stars do, but to quietly fade into white dwarfs, cold, dark, quiet. That is how the Stelliferous Era ends, not with a bang, with a slow dimming to black. Now the universe enters its next great phase, the degenerate era. After the last star has faded, 100 trillion years from now, give or take, what remains are stellar remnants, white dwarfs cooling toward black dwarfs over unimaginable timescales, neutron stars, and black holes. The degenerate era is named for the quantum mechanical state of the matter in white dwarfs and neutron stars. Degenerate matter, held up not by heat and fusion pressure, but by the Pauli exclusion principle, the quantum rule that says two identical fermions cannot occupy the same quantum state at the same time. The electrons in a white dwarf resist compression not because they are hot, but because they are, in a quantum sense, not permitted to get any closer together. It is the universe following its own rules, even in the dark. In the degenerate era, the sky is not black exactly. The cooling white dwarfs and neutron stars radiate a little, infrared, and radio wavelengths mostly, growing ever fainter. But there is no starlight in any meaningful sense. No nuclear fires. No new photons from fusion. Just the slow leak of residual heat into space, and the slow expansion of that space carrying everything farther apart. How long does the degenerate era last? It depends on something we do not yet know. There is a theoretical prediction arising from grand unified theories. Those attempts to describe the strong, weak, and electromagnetic forces as manifestations of a single underlying force at very high energies, that protons themselves are not perfectly stable, that they eventually decay into lighter particles, releasing a small amount of energy in the process. If proton decay happens, the timescale is thought to be something like 10 to the power of 34 years, or possibly much longer, depending on which version of the theory you prefer. Written out with zeros, that number would take more space than this script has room for. But here is the critical caveat: proton decay has never been observed. Experiments, most famously at the Super Kamiokande detector in Japan, a vast underground tank of ultra-pure water surrounded by sensitive light detectors, waiting patiently for the faint flash that a decaying proton would produce, have been watching for decades. They have set lower limits on the proton's lifetime. Those limits are enormous, but so far, no proton has been caught in the act of decaying. The current experimental lower limit on the proton's lifetime is roughly 10 to the 34 years, which means if protons do decay, they live at least that long, but perhaps they do not decay at all. Perhaps the grand unified theories that predict it are wrong or incomplete. We do not know. So proton decay is flagged properly as theoretical, as a possibility, as what might happen if our best guess about deep physics turns out to be right, not a measured fact, an extrapolation. If proton decay does occur on those timescales, then after about 10 to the 34 years, the white dwarfs and neutron stars themselves would slowly dissolve. The matter composing them would decay away particle by particle until eventually there is nothing left of ordinary matter at all. If proton decay does not occur, if protons are truly stable, then the white dwarfs and neutron stars persist essentially forever, cooling toward absolute zero in the dark until other processes claim them on even longer timescales. Either way, by this point in the story, we have arrived somewhere very strange, somewhere the human mind was not really built to navigate. The timescales involved exceed anything in our experience so thoroughly that they require a kind of deliberate letting go to even approach. But there is one more era to name before we reach the final silence. The black hole era. Black holes do not consume matter in their vicinity as quickly as science fiction sometimes suggests. They sit and wait, but they are, in an important sense, the most durable objects the universe produces. If proton decay dissolves ordinary matter, the black holes remain, built not of protons and neutrons, but of curved space-time itself, and space-time does not decay. Black holes of various masses formed from the deaths of massive stars or from the mergers of smaller black holes or from the supermassive black holes at the centers of galaxies, they persist. They grow slowly by absorbing whatever matter drifts into them over cosmic time. And they wait. But here is the subtle and remarkable thing about black holes. They are not perfectly permanent either. Stephen Hawking in 1974 proposed that black holes very slowly emit radiation, not from inside the event horizon, nothing crosses that threshold outward, but from the quantum behavior of space at the horizon's edge. The details involve quantum field theory and virtual particle pairs and the geometry of curved space-time, and they are genuinely deep and complex. But the upshot is this: black holes are not quite perfectly black. They emit a tiny, faint, cold trickle of thermal radiation, and in doing so they lose mass, slowly. Extraordinarily slowly. The rate of emission depends on the mass of the black hole. Smaller black holes radiate faster. Larger ones radiate almost undetectably, slowly. For a black hole of stellar mass, a few times the mass of the Sun, the evaporation time, if Hawking radiation is real, is something like 10 to the 67 years. That is already a number so large it loses meaning against our ordinary intuitions. For the supermassive black holes at the centers of galaxies, objects measuring millions or billions of solar masses, the evaporation time extends to something like 10 to the 100th years, sometimes written as a googol years, since a googol is 10 to the power of 100 zeros, after a number 1. In that unimaginably distant era, the last black holes will have finished radiating. The final one, some enormous supermassive remnant of what was once a galaxy's core, will emit its last photon and disappear, not with an explosion, with a quiet, final pulse of radiation, and then nothing. And then the dark era. We should be honest about this. Everything from the degenerate era onward is theoretical. The models of physics that carry us this far forward are extrapolations. They assume the laws of physics as we currently understand them continue to apply, that no new physics emerges, that the structure of reality does not hold surprises we cannot yet imagine. Any or all of those assumptions may be wrong. Physics has surprised us before. It has surprised us repeatedly and dramatically, as you've heard throughout this long, quiet night. But under the physics we know, the universe after the last black hole evaporates is a place of extraordinary stillness, a cold, enormously expanded space. No stars, no planets, no black holes, no ordinary matter, if proton decay has done its work. Only a thin scattering of elementary particles, electrons, positrons, photons, neutrinos, perhaps some exotic remnants we cannot yet predict, drifting ever farther apart in a universe that continues to expand, continues to cool, continues to approach what physicists call maximum entropy. Entropy. Think of it this way. Imagine a child's bedroom perfectly organized, books in order, toys in their places, every sock paired and folded. That is a low entropy state. Ordered, specific, unlikely. Now imagine the same room after a month of normal childhood living. Disorder everywhere. That is a higher entropy state. And here is the thing about entropy. It tends to increase on its own. The room does not organize itself. You have to put energy into organizing it. Entropy, left alone, goes one way. The universe is the same. It began in an extraordinarily low entropy state. It had the precise, hot, dense conditions of the very early cosmos. And it has been moving ever since toward higher entropy, toward greater disorder. Stars are actually a part of this process. They take the low entropy configuration of compressed hydrogen and convert it irreversibly into helium and heavier elements and heat radiated into space, which is a much higher entropy arrangement. Every fire that burns increases the universe's entropy. At the end of all things, the universe reaches something close to maximum entropy. Everything is as spread out as it can be. Everything is as cold as it can be. Everything is as uniform as it can be. There is no more useful energy available, no gradients to drive processes, no concentrations of anything to power reactions. This is sometimes called the heat death of the universe. The name is counterintuitive. It is not hot. It is cold, and it is death only in the sense that nothing more can happen. It is the final equilibrium, the ultimate rest. Nothing moves toward anything. There is no toward, there is just expansion. Expansion of a cold, dark, nearly empty space, carrying the last thin remnant of particles farther and farther apart, until even the idea of distance loses its usual meaning. That is the end of the story as best we can tell. It is very quiet, and it is very far away. Let's come back to the present for a moment. Let's breathe. Because there is something remarkable in all of this. And it has been building quietly throughout the night, and I want to name it clearly before we close. There is a way of mapping this entire story, this whole arc, from the first nanosecond to the last dim particle in the dark era, onto something more graspable. A calendar. The astronomer Carl Sagan described something like this, and it has stayed in the imagination ever since. Imagine compressing the entire eventful timeline of the universe. Let's use the Stelliferous Era as our denominator, the time from the first stars to the last, roughly 100 trillion years, into a single calendar year. 12 months. 365 days. In this calendar, the first stars light up on the very first day of January. The entire 13.8 billion years we've traveled through tonight, all of it, The Big Bang's first second, the Dark Ages, the cosmic dawn, the first galaxies, the sun's formation, the whole of Earth's history, the rise of life, the evolution of every species that ever lived, the entirety of human civilization. All of it is compressed into the first hours of January the 1st. We are not at the end of the year, we are not even through the first morning. We are somewhere in the very early hours of January, and the rest of the year stretches ahead. 100 trillion years of slower and slower star formation, dim red suns burning for trillions of years in the quiet of diminishing galaxies, and then the long dark, and finally the last photon from the last evaporating black hole, somewhere in the final seconds of December the 31st of this imaginary year. On that calendar, Carl Sagan noted that all of recorded human history, every dynasty, every empire, every war and treaty and cathedral and equation and symphony fits into roughly the last 14 seconds of December 31st. The entirety of what we call civilization is the last 14 seconds of the year. But here is the reframe that the title of this video was reaching toward all along. If you are using the full Stelliferous Era as the calendar, the current moment is not in late December. It is not even in October or June or March. The current moment is in the very first hours of January the 1st. The universe's story is not mostly behind us, it is almost entirely ahead. We live in the brief, bright childhood of a cosmos that will run, by one reasonable measure, for roughly 100 trillion years. We are 13.8 billion years in. That is, to put it plainly, about 1/10,000th of the Stelliferous Era. If the whole star-bearing age were a human lifetime of 80 years, we would be living in roughly the first 3 days. And those first days are the bright ones, the warm ones, the ones when the sky is full of stars and galaxies and light, the ones when new suns are still being born, though fewer now than at the peak. The ones when a small planet orbiting a middle-aged star can still have liquid water on its surface and chemistry complex enough to produce something that lies awake in the dark and wonders about the cosmos. The peak of star formation to the cosmic noon, the brightest the universe will ever be, was 10 billion years ago when the sky blazed with newborn galaxies and the rate of stellar birth was 10 times what it is now. By the clocks of the universe, that brilliant noon is a memory. We live in the afternoon. A long, quiet, still beautiful afternoon with enough light left for all of recorded history and millions of generations to come, but an afternoon nonetheless. And in the coming night, in the trillions of years of dimming stars, and then the degenerate dark, and then the black hole era, and then the final silence, there will be no one, as far as we can guess, to see any of it. The conditions that produced us, that produced life and minds and questions, exist in this early window. When the last red dwarf finally cools in roughly 100 trillion years, it will not be lighting any civilization. The universe will have moved on to its long, cold, solitary old age. So here is the thing. Right now, in this brief, improbable moment, the universe is not just populated with stars, it is populated, in at least one corner, with something much stranger than stars. It is populated with matter that has organized itself to the point of asking questions. Matter that wants to understand. Matter that lies down in the dark and listens to the sound of the universe's own past. The cosmic microwave background, that ancient afterglow of the first light, still washing through this room right now as you rest. A reminder that the whole story is still here, still real, still ringing. Your atoms were inside stars. Not metaphorically, literally. The carbon in the molecules of your cells, the oxygen you just breathed, the iron your heart is pumping in your blood right now. Those atoms were fused in stellar cores billions of years before the sun existed. They were scattered into space when those stars died. They drifted through the galaxy for a time, perhaps millions of years, perhaps longer, and then they were gathered by gravity into the cloud that became the Sun and its planets. And some of them ended up in the water of a young ocean. And in that ocean, chemistry happened. Over a long time, a very long time, chemistry produced biology, and biology produced complexity, and complexity produced something that eventually became a nervous system capable of lying very still in a dark room and following a slow story about the history of everything. You are not a bystander to the universe's history. You are made of it. The carbon in you was inside a star that is now long dead and cold. The hydrogen in you, the single proton hydrogen that makes up the water in your body, that bonds with oxygen to make every cell mostly water. That hydrogen is older still. It was forged in the first 20 minutes after the Big Bang in the nucleosynthesis we talked about so many hours ago tonight, when the universe was young and hot and smaller than a solar system. That hydrogen has been here for 13.8 billion years. It was here before the Earth existed. It was here before the Sun. It was part of the primordial fog that filled the dark universe before the first stars ignited. You are carrying the oldest atoms in the universe, in your body, right now. Take a moment with that if you like. There's no rush. The hydrogen in the water in your body is older than the Milky Way. It is older than the Sun by 9 billion years. It drifted through the cosmic dark ages. It was there when the first stars lit up. It survived the rionization of the universe. It was pulled into a molecular cloud, into a protostellar disk, into a young ocean, into life, into you. That is an almost unreasonable chain of events. And yet here it is. Here you are. There is something else worth sitting with as the night gets late and the story closes. We have been honest tonight about what we don't know, the nature of dark energy, unknown, the mechanism of baryogenesis, why matter outnumbered antimatter by that 1 in a billion margin that made existence possible, unsolved. The exact fate of the expanding universe in the very long run, uncertain, dependent on physics we do not yet have. Whether proton decay occurs on those enormous timescales, unconfirmed. Whether Hawking radiation is real, whether the heat death scenario holds, whether the laws of physics as we understand them continue to apply across timescales that dwarf even the age of the universe. We do not know. The universe keeps its deepest secrets. But here is what we do know. We know that about 13.8 billion years ago, in conditions of almost incomprehensible heat and density, a universe began. Or at least that is where our measurements start, at the point our physics can reach. We know that in the first fractions of a second, the forces that govern everything froze into their distinct forms. We know that in the first 20 minutes, the light elements were forged. We know that about 380,000 years later, the universe cooled enough for atoms to form and released a wash of light that is still traveling through space today, still passing through your walls, your body, this room, right now, at this moment. We know that the universe spent over 100 million years in total darkness before the first stars lit up. We know that those first stars seeded the cosmos with the heavier elements that eventually made planets and life possible. We know that star formation peaked about 10 billion years ago and has been declining since. We know that our Sun formed 4.6 billion years ago from the remnants of earlier stars, that life on Earth began not long after, and that the atoms of living things have been rearranging themselves here in an increasingly complex dance ever since. We know that the expansion of space is accelerating, and that something we cannot identify, comprising roughly 68% of the universe's total energy, is responsible. We know that another 27% of the universe is dark matter, also unidentified, present in the halos around galaxies and in the structure of the cosmic web, felt through gravity but not through light. And we know that everything we have ever seen, every star and galaxy and planet and person, is about 5% of what is out there. We are the 5% that became curious about the other 95%. And we know that the story is not over, not by any reasonable measure. The Stelliferous Era has barely begun. The stars will keep burning for 100 trillion years. The universe is not old, it is young. It is, by the light of its own eventual timeline, a newborn thing, still bright, still warm, still making stars, still full of the light and chemistry that here in at least one corner of one galaxy produced this night, this question, this listening. Where are you right now? I asked that at the beginning of tonight, and I mean it just as simply now as I did then. Wherever you are, whatever corner of this small, improbable planet you're lying in, whatever time it is in your part of the world, whether there's still a light on or whether you've been drifting in and out for the last hour, wherever you are inside the story. Not at its end, not at its climax, which was 10 billion years ago when the cosmos blazed at peak light. Not even at its midpoint.
You are near its beginning. The fire is still burning. It is burning a little lower than it was at noon, yes. The peak is behind the universe, but by every clock that matters on a human scale, there is warmth enough and light enough and time enough for whatever comes next, for whoever or whatever the universe produces in the long, slow, magnificent, dimming afternoon of its stellar youth.
And then eventually, yes, the night comes, not tonight, not for time scales that make every number we've used tonight seem small, but it comes. The last star fades, the last black hole exhales its final quiet breath of Hawking radiation, and the universe settles into the cold, dark, gentle entropy of its old age. Not death, exactly. Just stillness. Just the final quiet after a very long and very extraordinary story. That is not sad, I think. Or it doesn't have to be. Everything ends, stars end, planets end, even black holes apparently end. Slowly, patiently, over incomprehensible timescales, but end. And everything that ends was real while it burned, real while it shone. The light from those first population Thray stars, those enormous blue giants that lit up the cosmic dawn 200 million years after the Big Bang, that light traveled outward into space, and some of it may still be traveling now, stretched by expansion into frequencies too low to see, carrying the record of fires that burned before the Earth existed. Everything that happened, happened. The universe does not take it back. Your atoms were real inside a star. The star was real. The light it made was real. The carbon it forged was real. And now you are real in this moment, in the early hours of the universe's long calendar, carrying those atoms, asking those questions, following this slow and quiet story to its end. That feels to Grandpa like something worth knowing, something worth carrying into sleep.
If you've been with me all night, through the first second and the dark ages and the cosmic dawn and the blazing noon and the long afternoon of the present and all the way out to the deep future and its quiet close, thank you for that. Truly, small channels like this one keep going because of listeners who stay, who find something worth finding in a long, quiet night like this. If tonight was one of those nights for you, a gentle like or a subscribe means more than you might think.
Small creators like me really do rely on your support to keep these journeys going, and if you'd like to leave a comment, or tell me where in the world you're listening from and what time it is in your corner of the night. I always love to know. The hydrogen in your body has been traveling for 13.8 billion years. It has a little farther to go yet. And tonight, for a little while, it was here, in the quiet, listening to the story of where it's been.
That's enough. That is somehow enough. Good night, kiddo. Grandpa'll leave the porch light on.